All right. So I guess we are nominally at the start of our time slot. So welcome to the Stack Club session. This is the third Stack Club session that we've had at PCWs over the last 3 years. So I'm Alex Sterlico-Wagner, and my co-coordinator of Stack Club is Greg Majeski at Stanford. Before we jump into this, I think people have seen this slide many times already this week. But this is just a reminder that we adhere to principles of kindness, trust, respect, and diversity and inclusion to try and provide a learning environment that's productive and promotes excellence. Any discriminatory behavior will not be tolerated. And if you witness any bullying, harassment, or aggression, please follow the code of conduct in reporting it. I believe we are recording this session. Yeah, I see the blinking red light. And so if you don't want to be recorded, please go ahead and turn off your video and audio now. Please use either Zoom or Slack for questions. I think preferably Slack so that we have a better record of those questions. And the Slack link is listed on the webpage for this session. And then additionally, please show your appreciation, give thumbs up, give applause, and give feedback. We have some really great presentations of Stack Club notebooks that have been put together by course participants, so let's show them some love. Okay, so the schedule for this session is that Greg and I put together a few slides just to give a brief overview of what the Stack Club is, what our goals are, and sort of what we've been trying to put together over the last few years. And then we're going to get into presentations from 4 of the participants in the inaugural Stack Club course, which was offered this spring. And so at that point, I'll turn it over to them to present their work. So what is the Stack Club? The Stack Club is focused around the concept that in order to do great science with Rubin Observatory data, we will need to understand how those data were produced and how to access and manipulate them. The Rubin Observatory data will be processed with something that's known as the science pipelines, which is a suite of software packages that you've probably heard quite a bit about over the course of this week and are affectionately known as the data management stack. Every science collaboration, so every scientist may not need to interact with the stack, and in fact, many scientists will be interacting with the catalogs directly. But we do expect that every science collaboration will benefit from some amount of stack experience, local scientific experts that have some deeper understanding of the tools and software that was used to process the data. In order to build this expertise, we wanted to start getting scientists to interact and learn about the stack now, embedding this experience within the science collaborations as best we could. And so the approach that the Stack Club follows is that the best way to learn something is by teaching it. And so the goal of the Stack Club has been to get members of the science collaborations to interact with the Rubin Science Platform and the data management stacks, and to build tutorials around those tools that will help both those members of the science collaborations learn how the tools work and help teach the next generation of scientists and science collaboration members how to interact with the stack. So this is just a snapshot of what the tools look like that the Stack Club interacts with. So one is the Rubin Observatory Science Platform, formerly the LSP, now the RSP, which is a Jupyter Hub, Jupyter Lab environment for interacting with the data management stack and the data products. This provides both terminal and notebook, IPython notebook, Jupyter notebook access to the data and software. Important to note is that several versions of the stack are actually preloaded on the RSP. So it bypasses the need to do private installations or wrangle with the dependencies of the code. For sharing notebooks and for documenting them, we use GitHub, a public GitHub repository. So all our work is in the public domain there. And if you're interested in getting involved, you can apply for membership at the following link here on the slides. So at the last PCW, we got feedback from several attenders, several members of the science collaborations, that it was perceived that the Stack Club was already too advanced for new participants. So the idea that we came up with was to start offering a Stack Club course that was focused on getting new participants involved and up to speed. So over the spring, we teamed up with some great instructors from the project and current Stack Club members to offer an 8-week course that spanned from, I think it was early May through late June. This was always planned to be an online course, and it just happened to coincide with the time period when everything else went online. So we were lucky in that regard. So you can see the overview of the sessions of the course. So we had 6 sessions that were focused on introductory material from various members of the project and the Stack Club. And then we had 2 sessions at the end where participants were encouraged to design their own projects and put together their own notebooks, which you'll be hearing a little bit more about later in this session. And all the material is online. All of the sessions were recorded. And so you can find that all at the GitHub URL at the bottom of this slide. So an example of one session, I just chose session 3 here, is a combination of short presentations, overviews of some of the tools and techniques, followed by hands-on interactions with the software and data products, either as pre-developed notebooks or as real-time coding tutorials. And so you can go look at all of the information that's on GitHub associated with each session here, and you can watch the videos of the sessions. They usually constitute some amount of introductory slide presentation material, followed by hands-on working through of notebooks or code. So just to note, participation in this first instance of the course was limited due to the resources that we had available. So we had 125 applications, and we were only able to offer participation to 20 members. We do plan to offer the course again soon. And it's really our hope that the Stack Club course and the Stack Club generally will help prepare the science collaborations and members of the science collaborations for involvement in commissioning and science verification. So it's our hope to get you comfortable with the Stack tools so that you can contribute to these efforts. All right, so I just wanted to end with a big thank you to all of the Stack Club course instructors, Simon, Yusra, Keith, Andrew, Imran, and Bryce, all donated their time to help put together some really great sessions to get people launched with the science platform and the Stack. And then we also had really great ongoing support from the project from Merlin and Melissa, Lee, Robert, Nate, Lauren, Meredith, John, Adam, Chris, and many, many others who have all really contributed to helping us learn the Stack and supporting our development as we go. It would not be possible without them. So I'm going to pause here for maybe a few questions. I think we're on schedule. And then I'll turn it over to Sarah. Sarah, I'm happy to share your slides here, or you can share them as well.
Alex, I'd also like to call out Christine Bannock, who was a little more behind the scenes, but she was instrumental and covered for Adam on a few occasions when we needed support and he was not available. So,
great, thanks. Thanks, Simon.
I don't see anything in the chat window, no questions, so.
Okay, all right. Well, if that's the case, we can move on ahead of schedule. So Sarah, would you like me to share my screen, or would you like to try and share?
I can try and share my screen. I hope I won't have problem with connection.
Good.
Okay. Can you see my slides?
Yes.
Okay, thank you. So, thank you. I'm Sara Bonito from the Italian National Institute of Astrophysics, INAF. I work at the Observatory of Palermo. This talk is in collaboration with Rachel Street and Marcus Rabus, and we will present the activity of the task force of the Transient Variable Star Science collaboration, focusing on the Rubin Science Platform used through the Stack Lab involvement and the application to science cases of interest of the Transient Variable Stars Science collaboration. And this is a list of other collaborators that provided us with material that I will show you in this talk. TVS Science collaboration consists of several groups and task forces. One of these is focused on the use of the platform and the Stack Lab involvement. And among the task forces of TVS, this is one with a higher number of members. This is a list of some of the many activities that we are working on in this task force. I will just briefly highlight some of them. We organized invited talks and participation to our regular telecons from data management scientists and Stack Lab experts. And I thank Leanne, Melissa, and Bryce for joining us. We also report our activity during international meeting. And last year, we presented our results during the workshop on the blending organized by also in Delaware. During the TVS and Stars and Milky Way and Local Volume Joint Workshop. Today, PCW, and in the future also during the meeting Rubin LSST at Europe that will be hosted in Italy, organized by INAF, and has been postponed. It was supposed to be in June 2020. It will be at the end of this year, of possibly our task force is to identify science cases of interest for the transient variable star science collaboration, which is very diverse, but often we can make use of the same common tools that I will show you here. A great deal of TVS science, in fact, will depend on the analysis of time series photometry from Rubin LSST. Just some example, the periodicity analysis will be necessary to detect and characterize eclipsing and pulsating variables. And eclipse modeling will be needed to determine the physical and orbital parameters of binary system, such as this white dwarf transit. And in a similar way for transient events such as supernovae, light curves, morphology, and decay time can be related to the physics of the explosion and subsequent processes. So a wide range of software packages already exist to perform this kind of analysis. And we can use test code, importing them and these packages in the Rubin Science Platform to analyze LSST data products. It is possible using the notebook aspect of the Rubin Science Platform to install our own software use. In fact, when we log in, we can work in our own virtual environment, and with the option to run both Jupyter notebooks and terminal. And this is what, in this case, Rachel Street have done in the terminal. As a demonstration, in the terminal prompt, it's possible to install existing packages for the analysis of light curves, in this case, the PyLima package, for microlensing events. But of course, you can install other packages in this straightforward, they're very easy, in particular through the pip install, or if they are
Sarah, I think we may have lost your audio.
Can you hear me? Can you hear me now? Also the previous, I can continue? Yeah. Okay, sorry. So I was saying that it is possible to access through the Butler, to the Butler system using the combining the measurement for multiple images. Here, there is an example. As a demonstration, light curve was built from randomly chosen star from the DECA-MID survey. It is here it's been performed by Rachel, the kind of point source point lens microlensing model fit that is typically used to assess whether a star was experiencing lensing. And on the left, there is the code in the Jupyter notebook aspect of the science platform. And on the right, you can see the produced spectrum model fitting. This is a DECAM image in the G band on the galactic bulge. This is another application of interest. And the galactic bulge is dense, so it can be useful for testing the pipeline in crowded regions. First, apply to this CCD frame. And it is possible to plot the calyps with additional information. In fact, the calyps has an image and a mask plane. The mask encodes additional information on the pixels. This is a zoom of the previous bulge image with Firefly plotting tool, which allow us to color code the mask plane on top of the image plane. And so we can identify detected objects or pixels marked as bad or saturated. And it is also possible to rerun source detection with different parameters. And so rerunning the detection algorithm with changed parameters of the same frame, it is possible for the same region here shown to detect more stars. And this work was done in particular by Marcus. We work in collaboration with the task force of TVS on crowded field photometry.
Sarah, I wonder, maybe you want to turn off your video. That's where your bandwidth would be used up for audio, because your audio is breaking up. Sorry to interrupt.
Yes, but I'm quite finishing, so.
Oh, okay, that's fine.
Let me check. Yeah, sorry, I have a bad connection now. So I was saying that we combined, as I show you here in the notebook aspect of the science platform, the color magnitude diagram catalog by the Gaia DR2 with proper motion information that we also derived in the portal aspect that we are learned to use in the very to use in the very beginning of the Stack Lab course. And here you can see the proper motion can identify the cluster, NGC 6569, and also on the right, we can identify the RR Lyra stars in this cluster. And in the notebook aspect, using the interactive visualization tool that we have learned during the course, this is the period luminosity relation for the RR Lyra stars in the Z band, and it should be the first time that we can derive this relation for the stars. We apply the same tools at very diverse science cases. In fact, we also are exploring other data, in this case CFHT data of young clusters, in this case the NGC 2264. We can discriminate accretors, which are the blue star with respect to the non-accretor stars, here indicating the yellow, the non-accretors, and in violet, the bluest accretors. And so selecting accretors in a young cluster, we can also perform follow-up spectroscopic analysis as done in the Gaia ISO survey contest. Here show you what we have derived for interactive visualization tool in the notebook aspect, where we can select a locus on the right of the plot that is the relation between the mass accretion rate and the width of the H-alpha spectral line. So we can connect their displacement in the cluster, but we can also correlate what we have also using spectroscopic analysis. Again, for a different subject, in this case, young stars, we can study the morphology of the light curves, as we have proposed in the white paper for the LST cadence optimization, where you can see on the left, in particular, a simulation what Rubin Observatory can detect for a young star with accretion and also experience.
Sarah, we may have lost you. Okay. So while we try and get Sarah back, maybe we can field any questions that may be here, or if anyone from the TVS team is online and wants to finish, I can share my screen and we can finish the slides. I think that Sarah was very close to done.
Yeah, I think that's right. She was on slide 24 of 27, so probably.
Okay, so maybe if Sarah is able to reconnect, we can let her show those last slides. But in the meantime, if we have any questions, we have a few minutes before we are on schedule, so we have a few minutes for questions.
Let me read one question here that
I think Sarah's back.
Oh, Sarah's back. Fine, great.
Hi, I'm very sorry. I'm now connected with my mobile. So I was actually concluding because if I don't know if you can share my last two slides, please.
Yeah, let me pull it up.
I'm sorry because now I'm with my mobile.
Yeah, don't worry about it. No,
thank you.
It does happen.
Okay. Was just the last couple of slides. I'm sorry, I hope not to run out of time. Yes, thank you. So we discussed this light curve that can be observed with the Rubin Observatory during last week hackathon. And the next slide, please. We can also perform the same analysis, not in a sample of statistical sample of young stars, but also selecting individual stars of interest, like the so-called XOR objects, which experience eruptive accretion bursts, as shown here. And in the next slide, please. You can see that we have starting just a test in the notebook aspect to study with the ZTF data from different survey and brokers, the light curves of the accretion burst occurred just last year. And in the next and my last slide, I will just thank you and leave you here with information on the on this task force in particular, and on the general TVS new website, where you can also find some information on the new group just formed on justice, equity, diversity, and inclusion. And I will thank you and stop you here.
Thank you, Sarah. Any questions for Sarah?
I don't see any questions in the chat window, so
maybe I can ask one. So it seems like you explored both the analysis of precursor data sets that were loaded into the RSP, as well as some working through image processing with the stack tools. For either of those, was there, what would you say was the biggest gain you had from the experience? Like what was the takeaway that you got from this?
Okay, I can say that we are, as a task force, we wanted to use a science platform using all the possible aspects, not just the portal and the notebook, but also different catalogs, data already ingested in the Butler, but also our own catalogs, as you are saying. So we are trying to explore all the different, also as a test, but also scientifically, because the TVS is so diverse in science interests. And so in some cases, we, as an example, we can say that we can perform the light curve of microlensing, as Rachel has done, using the DECAM, its survey already ingested, or the DECAM of the bulge for crowded field photometry. But in the case of young stars, I found that we need to import some of our own catalogs to explore the color magnitude diagrams and light curves. So up to now, it depends on your science case of interest. But of course, there are already a lot of information in the science platform and software that can be used. But we also explore the possibility to import the software. So the message is that there is very rich content in the Rubin Science Platform. We learn a lot of tools during the Stack Lab course, and I thank all the tutors for that. And I can say that I have learned a lot in a small amount of time, and thank you for the experience. Thank you.
Great, thanks. Okay, so I'm gonna stop sharing my screen again. And I'll turn it over to our next set of presenters, who I think are Aaron and Nishkia. Am I remembering the schedule correctly? Let's say that that's the case. Okay.
We've got a general question in the Slack channel. What what kind of data are in the repository for the Stack Club? Are they real data or simulated data?
So yeah, great question. So there's quite a variety of data there. I would say right now the dominant fraction of the data there are reprocessing of HSC or DCAM data, which is real data, but we also have real data from the LSST camera, which is test stand data. And we do have some simulated data from the Data Challenge 2 that the Dark Energy Science Collaboration ran. And then in addition, a lot of the data that Sarah was showing was data that she ingested, she uploaded into the science platform to analyze. Okay, thanks for that question. So turning it back over to Erin and Nushkia, go ahead and take it away.
Thank you. Thanks, Alex. And so I will start the presentation. We're going to present our notebook. I was working with Erin, and as well, this was also a project for the LSST Stack Club course. So to introduce our notebook, we decided to do a small project on showing how to compute a surface brightness profile of a galaxy given its coordinates. So to do this, we had to do many things. And to summarize, the first thing is we needed to locate the object in the available repositories in the stack. And then we created a thumbnail of the object for the analysis. Then we also wanted to create some nice color images of the galaxies because of the galaxy, we export just one object because we think that it helps a lot with the analysis when you have to create masks and segmentation maps to mask out the sources so that we could estimate the background of the image and then ultimately get the surface brightness profile. So that's basically the goal of our notebook. So we have various packages that we need to install for this. They're all grouped here in this cell. I won't go over it, but these are standard packages that usually when you want to access the data and you want to do certain tasks, you can do it in the platform. And we also have a number of functions in order to create the surface brightness profiles as well as RGB images. This is a function to make elliptical coordinates for the galaxy given its center in the image and its position angle and ellipticity. This is a function to create the surface brightness profile. Aaron will talk more about it in the later part of the talk. But the essential idea is to create averaged profiles along elliptical annuli from the center of the galaxy to the outskirts. And also we made a function to create a color image. We were using an AstroPy function called make-lookturn RGB. But we also improved that function a little bit by adding a sort of scaling parameter where we can choose which of the RG and B channels we want to enhance or not. I'll talk about that a bit later. So to select the galaxy by coordinates, we got help from Yusra to try to figure out a way you input the coordinates of the objects and then find which repository in the Stack Club you can actually find this galaxy or object. So this can be generalized. We were using a PDR2 repository because it's the most complete one now. And basically, I mean, this is just a function, very short script to look at the repositories in this PDR2 and then find out, given the coordinates, find out where the galaxy is. And so then you get back the tract and the patch. And then this is a standard also to basically get the galaxy using the butler. And then we get the calyx of all the bands here. And then we get basically the galaxy images in all the bands. So this is in G, R2, etc. So this is the galaxy we're working with. And to create the RGB image, so basically we need to create an exposure. And then I just want to show a quick comparison. So this is the original Make Lupton RGB image. And you can see that it somehow produces very red image, even though you expect a spiral galaxy to have blue ones. So this is something that I've actually been working on in my first year of PhD, and I wanted to improve this function, and I thought this was a good platform to introduce it. So basically I just scale each of the channels in a way that I want to until I get something that looks nice, basically. And this was something that I learned from Lee Kelvin's plot fits program in R that was told to me by one of my colleagues at my institute. So I kind of Pythonized it to make it look, give very nice images. So this is the result. And then I also just basically like to make a grayscale background. And this is basically in Python, you can create a luminance channel. So you have RGB, but then you can also give a luminance channel to show the transparency. So here I'm just using the sum of all the three bands. So you get a very nice image. And what's overplotted here is the ellipse of the galaxy in pink. This I just did it visually to get the global shape of the object. And the grayscale is very nice because you can see where the edge of the object is, if there is anything, and it gives you a better contrast so that you can see how you are measuring these kind of parameters. And now I'm going to give it over to Aaron, who's going to talk about masking.
Yes, so one thing when you want to do at least careful surface photometry is you need to make sure that you're not including sources that are not part of the object that you're doing photometry on. So evidently, in order to do that, you need to mask out things that you don't want. So I spent a lot of time thinking about various ways to do this from the stack, and we ended up doing kind of a hybrid semi-automated process. So the first part of this, we used the detection task, which is built in. We're using a very low threshold here, just 1 sigma above the background, which we'll show later is still not quite sufficient for our purposes. So we create the task, we run it. This produces a table of detections, which all have these lovely footprints, which are identifiable by their spans. And so using all of these things, this big block of code down here basically runs through each of these, finds and isolates the footprint that belongs to the target galaxy, increases the size of the footprints using the dilation function, which is also just included in this. It's very nice. And then pumps out a new image in which all of the pixels that we wanted masked are replaced with nan, not a number, so that they're easily ignored. So you can see the output of this down here. So on the left is the original image without any masking. On the right is a masked image excluding the galaxy, so just doing things outside of the galaxy's footprint. You'll notice that that also removes a lot of background galaxies which are connected to it, so we'll talk about that in a bit. And then finally on the right, this is the total mask where we mask everything out, which we are going to use to estimate our local sky background. You want to scroll down there? Okay, so in order to mask some of the things that are embedded within the galaxy, or at least part of that same footprint, I attempted to do this using Scarlet. Ran into a number of issues with the current implementation of Scarlet in the stack, so I was directed by Fred Mullenkamp to a code by Remy Joseph, which uses Scarlet to, it basically does a kind of wavelet decomposition of the image, which removes most of the large-scale diffuse light and pinpoints a lot of the higher surface brightness objects, and then runs the Python implementation of Sextractor on that, called SEP. And so this pumps out a Sextractor table of detections of all of the sources that are embedded within your galaxy, as well as other things. So we use this output, because it's just a Sextractor table, it doesn't contain the detailed shapes of the detections, it just gives you axis ratios and position angle and things like that. So the resulting mask ends up looking like this. So you can see it finds almost everything. It finds all the things embedded within the galaxy very nicely, but of course, it also finds things that you don't want to mask, like the galactic bar and the bulge and parts of the spiral arms. So this is where the semi-automated part comes in. We wanted to remove the masks that we didn't want included in order to do the proper surface photometry, and also just adjust some of the other masks to help improve it even more. So I'll take it back to Nushkia.
Thank you, Aaron. To do the manual masking part, because we want to unmask this part and then potentially also improve the masking of this area, which is not masked properly in the original mask. And I talked to Keith, and then he pointed me to HoloViews. I struggled a little bit because at first I thought it was bokeh only, and then I forgot about HoloViews. But then HoloViews is very nice because you can create a sort of panels like this. And here in this side, I've plotted the ellipses that you saw before, and on top, the centers of all the detections, okay? And basically with HoloViews, you can select region. So I can make a selection, right? And it glows. So the points that you select, I've made it look like it glows because it looks very nice. And then it tells you which are the points that you've selected. So for example, I can make a selection in like this. And then I know this is what I want to unmask. So I've written a little program so that you can unmask these points, these detections. And then this is how the mask looks like. So I've basically unmasked all of that central deblended regions. And then the same thing you can do, but for masking. So I want to mask this region here. So then I created another separate HoloView panel. And basically you can use the lasso select. You can put your mouse and select which points you want. And it's cool. And basically you can unmask it in the same way. And you can mask it, sorry, and then this is kind of our final mask. So this is showing you the unmasked regions and the masked regions. I've written it in a way that you can reset all your selections. So if you go back to the first cell, you can basically reset everything and then, sorry, this one here, you can reset everything and then make more selections. The only thing is that I haven't figured out whether with HoloViews, you can make more than one selection at the same time. So it seems that when you have to select indices, you have to do it one at a time. But no problem, because you just select and then you mask. You select and then you mask again. You can do that many times you want. So this is just an example to show. And then the final mask looks like this. And the final thing is that we can use this updated mask to create the, compute the sky background for the galaxy. And basically, just to summarize what we did is we took only the regions of the image that are undetected, and we created equal area boxes around on this image of only the undetected pixels, and then computed what is the mean flux in those regions. And basically, we have the mean background value and the standard deviation value. And using these values, you can then get an idea of what is the limiting surface brightness of the image. And this is computed here using 3 sigma of the standard deviation of the background. So I'll leave it now to Aaron.
Yep, so finally the last thing was to actually make the surface brightness profile. So we did this using basically some codes that I've had lying around on my computer for a couple of years now, which I modified. They work relatively quickly. They only do photometry on the part of the image that's relevant, so you can run it blindingly fast in the stack if you want. If you're not satisfied though, you can always modify it. But essentially it just pumps out a radius array, the mean surface brightness and the median surface brightness as a function of radius. So I think you can just jump down to the plots. Yes. So here's the results. The left is the original image. The middle panel shows the image with the masks as well as a number of interesting isophotal radii. And then on the right is the actual radial profile. So you can see it looks pretty good. It's the standard sort of radial profile you get for a barred galaxy like this. That first hump there is an inner ring. You have a gap between the inner and the outer ring, which is the magenta. And then there's another hump just beyond that, which is the outer ring. Now we noticed as well marked in red at the end here, that there seems to be a bit of over subtraction going on in the very outskirts, starting at something like maybe 26.5, 27, which we're curious about, but that's a topic for another day. So I think that's about everything. So we just wanted to thank everyone again, everybody who gave us help with this. It took a very long time to put together because it ended up being a lot more complicated than I thought it would originally be. So thanks again. I guess we'll take your questions now.
Yeah, thank you very much.
Thanks. There's a lot of really positive feedback on Slack. And
should we stop sharing or?
if you can stop sharing. I think
Okay,
we may need to move on to the next presentation, and then maybe we can hold some questions till the end, or they can be asked on Slack and Zoom. It's a really, really cool notebook. People are already asking where they can find it. Okay, great. So our next presentation is from Ismail.
Yes, I'm going to share my screen.
Great.
How much time do I have, by the way?
So nominally you have 13 minutes.
Okay, great. Can you see my slides?
Yes.
And they switch? Yes, okay, great. Okay, yeah, so I'm gonna talk about this Scarlet notebook tutorial that's part of the Stack Club. This notebook was created by Fred Molkamp, and as part of the project for the Stack Club course, I kind of revived it and added a couple of things to it. Yeah, so I just want to give a quick description of Scarlet for people who are not familiar, just to give some context. So Scarlet is the blender or source separation algorithm for multi-band image data. It uses something called constraint matrix factorization to model sources using non-parametric morphology, and it accounts for their spectral energy distribution. And it also uses some fancy optimization methods like proximal gradient descent to do like the optimization and find like the best morphology or SED that fits the data. If you want to learn more about Scarlet, I posted some GitHub links in here about the GitHub code and the documentation if you're interested. And then some of the core concepts from Scarlet that will appear in the notebook. There's this thing called frames that you can basically think about objects that contain metadata about basically the images you want to analyze and the models that you want to fit to those images. So for example, observations is also a frame, and that frame might contain things like weights, PSF, channels or bands, WCS information. So that will all be stored in like the corresponding frame of the observations. And there's also a modeling frame, which has basically the model that you want to use to fit to your observations. Yeah, and then the other component that appears in the notebook that I'll talk about is sources, which is basically the different components that you will use to fit your model to the observations. So for example, stars are point source in Scarlet, for example, and galaxies can be extended sources. Yeah, so yeah, I won't go through too many details, but just to give you a flavor of Scarlet. Yeah, and so I'm gonna talk about this tutorial notebook that Fred Molkamp created, and then I just added a couple of things and revive it to run with the current Stack version, LSD pipeline version. It uses a preprocessed data set from HST Cosmos of some galaxies or blends of galaxies that were detected using the LSD pipeline, although that part is not shown in this tutorial, just like the actual use of Scarlet. Yeah, and the goal of this tutorial notebook is just to see how the different components of Scarlet fit together to blend some real galaxy images. And then Fred had a couple of comments about this notebook. So he just wanted to mention that Scarlet has an upcoming update that will change some of the API, and that there's two versions of Scarlet that you can potentially use. One of them is in the GitHub, that has the most updated version, and you can use it for a lot of complicated cases. And then there's one version in the LSST pipelines that's only to be used to handle it handles most blends well, but doesn't handle some of the more complicated sources. So if you want to handle more complicated sources, you can use the GitHub version of Scarlet. That's the one that I'm going to be demonstrating in this tutorial. Okay, so if you want to look at this notebook, I just linked it in the slides that you can find in the session post. And I'm just going to switch my screen share because I like the IPython notebook view better than the PDF I have. To share the notebook. Can you guys see the notebook now? Yeah. Okay, great. Yeah, so yeah, just a short tutorial to demonstrate how to use Scarlet. I demonstrate how to configure and kind of set up Scarlet to do the fit that you want. And yeah, and we'll see various model assumptions that you can use. And applying constraints is something that will be updated and added to the notebook, but it's not in the current implementation. Okay, so yeah, so we just have your basic setup for using the LSST pipelines and some packages that will use standard kind of AstroPy, RGB images, and some functions from Scarlet. So the first thing in the notebook is to load the data. And so this shared directory that you can find in NERSC contains some of the blends that were detected with the LSST pipelines and that you can access. So we just load the images, the weights, the peaks, because we already run detection on them, and the PSFs, and then with the bands that are included for this data. And this is all information that Scarlet needs to do the deblending. Then we get an estimate of the background from the images. And then Scarlet has its own kind of normalization that it uses for the images called an async mapping. And I won't go into details for what that is exactly or how it's used, but you can see more information in the Scarlet tutorial in the documentation. So yeah, so I loaded some images. So here Scarlet uses its own internal function to kind of change that 5-band image to a 3-channel image and be able to display it. And here I'm just showing, yeah, just doing that normalization into 3 channels and displaying the image as you would plot any normal NumPy array. So here's the image, just a preview that we'll be working with. And then here's also kind of a function that just uses matplotlib to also plot the PSFs across the bands that were loaded in case you also want to inspect the PSFs. And then I guess to actually do the fit for Scarlet, as I mentioned earlier, there's 2 frames that we need to define, a modeling frame and an observational frame, which contains the metadata for the model and the observation. So to do that, we first have to define for our model frame what the PSF is going to be for the model. And so in the Scarlet documentation, and here it's recommended to use a small Gaussian PSF that usually works well for a lot of fits. So you just specify the PSF and its shape, and you normalize it. And then we also normalize the PSFs that were loaded from the observations or from the data. And yeah, so this is where we create our model frame. As you can see, it has the same shape as the images that were loaded, but we add in the model PSF because that's also optimized. And we add the filters or the bands that are used. And then we also specify the observational frame, which has the actual images, the actual PSFs that were loaded earlier, and the weights. So that's how they're different. And then we need to set it up by matching it to the modeling frame. so that we can later use this frame to fit this observation. Okay, so now that we have like those two frames, we can actually initialize, tell Scarlet what sources we want to fit to the image. So the way to do that is by using one of the sources that is in Scarlet. So extended sources is a good source to use for like galaxies and things like that. So we load them and we specify the detected peaks and the modeling frame and the observation, and then that's how we create our sources. And these peaks were detected from the LST pipelines and were also loaded with the data. And then Scarlet also has some nice functions to kind of like display things as you go. So here I'm just like displaying the initialized sources and kind of like which observation, and in observation, which source it's going to correspond to. But this is like an initialization, so it's not fitted yet. But this is how it looks like now, and you can also see the SED. And there's also some exercises in the notebook that you can look at as well, but I won't go through them now. Okay, and so now that we like set up like the sources and the two frames, we're ready to deblend the scene. So the first step is to create a Scarlet.blend object that takes in the sources that you're going to fit in the observations. And once you have that, you just call blend.fit and you specify the maximum number of iterations and your the tolerance or how small you want your residuals to be. And then Scarlet basically does the fit for you. And here's like a log likelihood plot showing convergence. You can run for more iterations to get better convergence. And yeah, and basically now that you did the fit, you're gonna get the blended image out of it. And so Scarlet can also display the fit that you used, that you resulted from the images that resulted from the fit via this show scene function. So you have the sources that are already changed according to the fit and the observations. And here you can see the residual, the render model, and it looks pretty good. Yeah, and then I also have a cell here to show what the show scene function is doing, but more explicitly, but it does the same thing. Yeah, and that's it for the tutorial notebook.
Great, thanks, Ismail.
Yeah.
And thank you to all of the presenters and participants in the course. It's really great to see how you've explored the stack. So just to re-emphasize, I would say, I don't want to say that all of the participants had no exposure to the stack beforehand, but people are talking very cavalierly about objects like butlers and Scarlet and CalExps and all of these terms, which coming into the course, I would say most participants had little concept of. And the feedback that I think we could receive now also is that these presentations are at levels that may seem like they are higher than what you understand from the outside. But this was in basically using the course, what the course put together. It's really impressive to see how comfortable people now are talking about the stack products and the stack processing. So I just want to emphasize, we weren't cherry picking experts and then teaching to them. We were actually trying to do the opposite. And I would say it's been very successful.
Let me add one more thing. If you would like to take a look on some of the lessons that were presented during the first 6 weeks of the course, those are all recorded, so you can actually take a look on those. And if you're interested at all, we probably, not 100% certain, but most likely will run a second instance of the course again in the future.
Yeah, I would say we're definitely going to run it again. It's to be determined exactly when it'll take place. Yeah. Any other questions, comments, things that we may have missed on Slack? And I think we're at the end of our hour. Hopefully,
Alex, just only one question or several questions that came up along the same line. What are the prerequisites to the course? Maybe you can say a couple of words about that.
So yeah, so for this first iteration of the course, because we were restricted on resources and we were trying to figure things out, we did put a participants who had some familiarity with Python beforehand. I think in the future, the goal of the Stack Club is not to teach Python. Sorry, I might be breaking up. But the hope is that, that people who are less familiar with Python still were able to get things out of the course from it. Beyond that, we asked for some familiarity with astronomy and a little bit of background on image processing, but that really wasn't, I mean, what goes into astronomical data analysis. But we didn't put any strict requirements on familiarity with Rubin Observatory or with the tools that are in existence now.
Imran, do you see any other questions on your side? Imran, if you're speaking, you're muted.
Sorry, we've got a question on Slack. Does Rubin OBS have a plan to provide a software or some sort of computing environment with all those useful packages?
Right, yeah, so this is a good thing to just emphasize is that the science platform, which is the combination of the data products and software, the plan is for the project to support that broadly for the community during operation. So not only the software, of course, is all public already on GitHub, but the environment itself within which these projects were being performed also is going to be open to the public. Okay, great. Thank you all. It was a pleasure to see all of the great work that came out of this. So thanks. Bye.
Thanks, everybody. Bye.